We're in Chapter 5 and Section 5.1, Local Extrema. We're going to ignore the mean value theorem in this course. Now that we've spent a lot of time learning basically every way to take the derivative of a function, we're going to apply this differentiation. And we're going to apply it in the mathematical sense. In particular, what we're working toward is being able to understand and even sketch the curve of a graph based on the function and its derivatives. Now, one of the first things we're going to learn about is just a fundamental concept in mathematics, maxima and minima. The local maximum of a function is the largest value within some neighborhood of x, right? Note that the local maximum is a y value, okay? And analogously, local minimum of a function is, again, a y value that is less than all f of x in some neighborhood of c. So if we just look at an example, let's do a detailed example of this. Create some axes, maybe some big axes going on over here. And we'll just have some graph. Maybe we'll do one of these guys. And let's bust out all the tricks in the book. And we'll do something like this. There's our function y equals f of x. We have some interesting values here. I'll call this guy a, b, c, d, and let's actually go ahead and do this for d. Make it a little more interesting, okay? This will be our e. Our function's f, so we'll go to g and h, okay? So just based off our definitions of local maxes and local mins, note that right here, f of a is a local maximum, right? If we take some neighborhood of a, maybe this one, and we look at the corresponding y values in that neighborhood, they're all less than or equal to f of a. Draw that a little bit nicer, right? So let's just, I guess let's get a chart going on here. Here's our local max values. Local minimum values, and then I guess over here we'll have neither. Okay, so anyway, f of a is definitely local max. F of b, well, if you notice, if you take some neighborhood of b, maybe this neighborhood, all the values here are at least f of b. So f of b is an example of a local minimum. Right? It's less than or equal to all the values in some neighborhood. Now, what about f of c? Well, f of c is not defined. So f of c doesn't even exist, so I'm not even going to put it anywhere. So I'll just write here, f of c does not exist, so it's certainly not a max or a min, but it's not even a thing. Okay? Now, what about f of d? Pause the video and think. Is this a max or a min? Local max or local min? Well, if you think about it, if we take, say, this neighborhood for the x values and look at the neighborhood for the y values, even though this function is clearly not continuous at d, f of d, which we'll just say equals f of b, is actually less than all the surrounding y values. So f of d is actually a local min, a very weird local min. Probably not one we're going to see too often, but it's a local min. Now, what about f of e? Well, no matter what neighborhood you take, and I just chose one, but you can choose whichever one you want, no matter what, f of e is always less than all of these values. Maybe I'll highlight them so they stand out. but it's also greater than all of these values. Oh, whoops, that was too many. These values. So no matter what, f of e is neither a local max nor a local min. So it's neither. What about f of g? Well, it's kind of a weird shape. It's not differential. F is not differentiable at g, right? But f of g is bigger than any of the points, right? In any of the other y values in the neighborhood. So it's a local max. And lastly, h, I may have missed that a little bit, but the point is that it's a local min. All right, so there you have it. Those are some visual examples of local maxes and local mins. Now, the issue is how do we find these local maxes and local mins? Well, we'll get into that a little later. But for right now, just looking at a graph, those are local maxes, those are local mins, and those are the neithers. Okay? Now, one thing we're going to focus on, now that we have an idea of local maxes and mins, what about the absolute maximum, which we typically talk about on an interval? So we say the absolute maximum on an interval is the largest y value on that interval. And then you might imagine the absolute minimum is, well, it's the same thing, except it's the lowest value on the interval, the lowest y value on the interval. So let's, I don't know, come up with another example. So if we have some kind of a graph right here, maybe I'll go like this. Well, let's try that again. Something like that. And we'll say the interval is from, let's just say this is from A to B. So we don't actually care about the stuff before. So what is the absolute maximum of this function? Well, the absolute maximum on the interval A to B is going to be, f of b, right? That is the absolute maximum because it's the largest y value on the interval from A to B. What about the absolute minimum on A to B? Well, it's going to be, in this case, we'll call this guy C. F of C, right? So we'll say abs max f of b, abs min f of c. Okay? Now, it turns out, I'm not sure how obvious. I think it's kind of obvious if you just try a couple of examples. But the extreme value theorem, I really should have let you fill this in. But anyway, the extreme value theorem states that if you have a continuous function on a closed interval, A to B, then a function always has an absolute maximum and it always has an absolute minimum. And again, if you just try to, like if you just consider some interval, I don't know, A to B, whatever, and you just draw a continuous function, I don't really care what you do. Well, no. I don't even know what you, sorry, that didn't look so nice, but like, whatever. Maybe I'll just make it like an actual function, right? Something like that, right? No matter what, it's got an absolute max, right? There's our C. And it's got our absolute min, right? Absolute max is f of c. Right? Try drawing something different from what I drew. You're not going to be able to come up with a function that, or a graph that does not have an absolute max or an absolute min. Now, I just want to point out that if f is not continuous on the interval from A to B, or if the interval is not closed, then we're not guaranteed that f contains an absolute max or absolute min. For example, if we have a function that's not continuous on A to B, we might have something like this. So let's see how we could get a non-absolute max, right? You could have something like this. Right? Not a continuous function on the interval. You say, well, hold on a second. Isn't some point there an absolute max? Well, no, it's not. Because any point you choose, maybe this is your C, well, I could have chosen this point, and that's a bit higher. And you can keep doing that because there's a hole, and the real numbers are continuous, so you can just sort of keep getting closer and closer. And similarly with the absolute min. Right, so there's just no absolute min or max. Okay. Now, what if our interval is not closed? Well, suppose we have an interval from A to B. Well, suppose that it's not closed, right? So we're not necessarily including A or B. Maybe our function is continuous, but if f is not defined at A, or we're not considering f defined at A, then we have that. And if f is not defined at B either, then we have that. And again, no absolute max or min. And that's all we've got for that.